Okay, for chapter 2, this PowerPoint covers about the atoms, molecules, and ions. So Dalton's atomic theory. Why it's called theory? If you look at like the scientific method, one of the steps, it's theory, and then after theory, if there is no exception to it, it's going to change to law. So when you have like hypothesis, then you have your experimentation. Then after the experimentation, you have theory, and then you have law. So if there's exceptions, it would stay as a theory. So the reason Dalton's atomic theory stayed as a theory, it's because there were some exceptions to it. Okay. So based on Dalton's atomic theory, it says that elements are composed of extremely small particles called atom, and that was correct. All atoms of a given element are identical, having same size, mass, and chemical property. Do you agree or disagree with the second statement? So what do you think about all atoms of given element are identical, having same size, mass, and chemical properties? Which part has been denied later? Any idea?
Isn't it
same size?
Same size.
Mm-hmm. They are okay. They are not definitely the same mass, right?
Yeah.
Same mass. So this part, it was denied later. When it was denied, it was after discovery of the radio activity, and then after finding out about the gamma rays, and then discovery of the neutrons, and they found that some atoms of the same element, they have different number of neutrons. They all have same number of protons, because if you change the number of protons, you're not dealing with the same atom anymore. It's going to be different atom. And the number of electrons is always equal to number of protons. Can you tell me why those numbers are the same? Why number of protons must be equal to number of electrons? Or under what condition they could be different?
I thought it was protons and neutrons had to be equal, and then protons and electrons can have different charges.
No, for the charges are different, but the number of proton and electrons are the same for any given atom under the condition that there is no charge. So if you're talking about like sodium with the charge, this is not atom, is called ion. Okay, this is the sodium ion. But if you're talking about sodium atom, the number of proton equals the number of electrons. But for sodium ion, number of protons is not equal to number of electrons. Which one is going to be greater for sodium ion? Electrons greater or protons greater? Since we know that protons, they have positive charge and electron is negative charge, in this case, number of protons is going to be greater than number of electrons. These symbols are very similar. So number has like 2 vertical line, and then not equal is just 1 vertical line. Just want to clarify that. Number of proton is greater than number of electron for sodium ion that has a positive charge. So number of neutron is different for isotopes. So atoms of the same element that they have same number of protons but different number of neutrons, they're classified or defined as isotopes. The time that Dalton expressed his theory, actually the radioactivity was not discovered, Neutrons were not discovered, and for that time it was like a big milestone in the history of the chemistry. But later on, when they found that there are isotopes for different isotopes for the same element, then they said, okay, this is going to stay as a theory, it's not going to change too long. So it's also kind of a practice for the scientific method. So, but elements are composed of extremely small particles. They are called atoms. That is true. All atoms of given elements are identical. It's not all identical because they have different mass, but they all have same number of protons. Okay. The atoms of one element are different from atoms of other element, and that is true. Yes, that is true. This is true. And then chemical property is the same. Chemical property is going to be the same, but the mass is not, and the size, because the size of the nucleus, it doesn't affect too much the size of the atom, because the size of the nucleus is like a small, like let's say a baseball in a baseball field. So you have the size of the atom, you know, the nucleus, that you have the protons and the neutrons inside the nucleus, then electrons are basically orbiting around the nucleus, is the more the number of electrons that is going to say what's the size of the atom, not the number of neutrons and protons. So this may be, but definitely not the mass, and not that they are not identical. Okay, so compounds. Compounds are atoms of more than one element. Combination of two or more atoms is going to give you a compound. The number of the elements is going to be always the same. The number of each atom in the molecule is going to be always the same. So if you have carbon dioxide, this is the example we had before, is going to be 1 carbon, 2 oxygen all the time. If you change that, the name is going to change, and then you have carbon monoxide. And if you have like a N2O, you have dinitrogen monoxide. But if you have NO, is nitrogen monoxide. If you have NO2, is a nitrogen dioxide. So if you change these numbers, it's going to change the name for the compound. The property is going to change. Chemical reaction only involves rearrangement of the atoms. Atoms are not created or destroyed in chemical reactions. Do you agree with this statement? Is it still true or not true? In a chemical reaction, only chemical reactions only involve rearrangement of the atoms. Atoms are not created or destroyed in chemical reaction. Still true for only routine chemical reactions or wet chemical reactions. But if you talk about nuclear reaction, that's also a chemical reaction, right? In a nuclear reaction, atoms are actually going to be destroyed. They can change. They are going to change to the to energy, or some part of the atom is going to change to energy using the E equals mc square. So that's the speed of the light. That's the mass, and this is the amount of energy that is coming when the mass changes for an atom. So before the discovery of nuclear reaction, this was correct. Now it's you have to put a condition for a wet chemical reactions or chemical reactions in the lab other than nuclear reaction. This is true, is only rearrangement, but for in nuclear reaction it has changed. So that's another question mark here. So we did have some question mark there also, and that made the Dalton's atomic theory to stay as theory. Law of multiple proportion. What does it mean? It means that if the proportion of the element or atoms of element in a compound changes, then you have different compound. Okay, so for the same compound, the numbers are the same. So carbon monoxide, if you take carbon monoxide, you have a container of carbon monoxide. Any molecule of carbon monoxide you reach is going to be one carbon, one oxygen. But if the ratio of oxygen to carbon changes, then you get 2 to 1, then you have a different compound. That's going to be carbon dioxide. So for multiple proportions, that means you have different compound. For the same compound, is the same ratio. For different compounds, the ratio is changing. Law of conservation of mass. The law of conservation of mass, that's another, it was like it states at the theory, because in a routine chemical reactions that does not involve nuclear reaction, mass of the reactant equals mass of product. But for the nuclear reaction only, mass of the reactant equals to mass of product plus energy. So the law of conservation of the mass, it's true, is a law. And then after this nuclear reaction, it got shaky. Then the solution was that the law of conservation of mass and energy. So it kind of combined the two. So when you combine the two, then it stays as a law, because it was a law. And then since anything that changes to law is expected, no change for it. And since there was a change, then scientists, they were very upset and confused about it, until actually Albert Einstein solved the problem and said that instead of law of conservation of the mass, when there is nuclear reactions involved, since mass changes to energy, a combined law, it's valid now. So we have the solution was actually help the scientists to get over that nightmare. Okay. Discovery of the subatomic particles was after discovery of the radioactivity. When you have with the radioactivity, I mean, the electrons were discovered using like a cathode ray with different any element that they had in the placed in the cathode ray. It would give same nature of the energy or the beams that was coming out. It was exactly the same. And then they figured out that this, like, every element contains this particle. The atoms of every element contains this particle. Then when they exposed this to a charged plates, electrons, they were actually attracted to the positive, and not they were repelled by the negative charges. And since they were repelled by negative charges, they were attracted to positive charge. They found that the charge for electron is negative. So it was discovered by J.J. Thomson, discovered the electron. J.J. Thomson was also found that the charge for electron was negative. And the next step of his discovery was that he found the ratio of mass to charge for the electron. So he found this ratio. He didn't find the mass, but he found this ratio. Then next scientist, you know how it works in science, is like if you look at the thesis or dissertation for someone who just graduated from this major with the PhD degree, and you look at the dissertation, last page of dissertation is going to say what are the recommendation, like future work. Basically, what that student could not finish is recommending for the next scientist or next PhD students to continue. So what is left off by one scientist, we always like admire whatever, all the discoveries by one scientist, but whatever is left, then the next scientist is going to continue the work and find out, okay, that maybe mass to charge ratio was not enough for scientists. We need to know what is the mass, what is the charge. So it was discovered by Millikan, the oil drop experiments, that he actually performed that experiment. And based on that experiment, he found the charge for the electron. When the charge was found, and since Thomson gave the ratio, since we had the ratio, we have the charge, is just a three variables in there, right? We have the ratio, we have the charge. Now we could, then the mass was calculated by Millikan. So discovery of the electron was happened by J.J. Thomson. The ratio was found for the charge to mass by J.J. Thomson, and the nature of the charge, which was negative, also was found by him. But the actual value for the charge was this experiment that it was actually done by Millikan. So he did this experiment to found the nature. I'm sorry, the exact charge, and then calculate the exact mass. So discovery of the radioactivity actually helped a lot scientists, all the chemists and physicists that they used for their research, and they found that the radioactive substance is going to, it was like emitting a beam of radiation, and then that radiation was either like attracted to positive or repelled by the positive charge, and then they could say that this is like a positive charge. So if it's positively charged, it's going to be attracted by negative plate. If it's attracted by negative plate, it's going to be positively charged. So it's kind of the opposite. So three types of rays were discovered: alpha, gamma, and beta. Alpha particles from a radioactive substance was attracted to the negatively charged plate. So they found that the charge for alpha particle was, positive. Beta is negative because it's attracted by the positively charged plate, is coming down. Gamma moved a straight line. If it moves a straight line, is not attracted by plus or minus charge. That means gamma was neutral. So these are the particles that they were discovered. And when it was discovered, then it was used later on by other scientists. So the radioactivity discovery, it was another like big milestone for the scientists. Then Ernest Rutherford was actually the one who used that. Okay, so this model was actually presented before Rutherford experiment. They said that you have the negative charges, and then you have the positive charge spread over the atom, or the size of the atom, or the space occupied by the atom. And this didn't last long, because right after this, if you look at the actual date, then right after that, maybe 1 year after that, Rutherford had his discovery or his experiment, and he actually proved that no, the negative charge, the mass is not spread like this, the green shade. That's not the mass of the atom. He proved that mass of the atom was actually condensed in the center of the atom. center of the atom, and how or what observation from his experiment yield him to this conclusion that the mass is condensed in the center, because he used the alpha particles. Okay, he used only the alpha particles. He could actually filter the other particles, so he used only the alpha particles and hit the gold foil, a tin gold foil, and these beams, the alpha particles, they were passing through this film. So he said that most of the atom is empty space because most of the beams are passing through. If it's not empty space, they will not pass through. Once in a while, they reflect, they bounce and they reflect. It's like you hit the ping pong ball to the wall. What happens? It comes back. It bounces back. When it hits the heavy object, it comes back. But if you throw the ping pong ball through air, it's not going to bounce back, right? It will pass through. But if it hits an object, it will come back. Since the bouncing back, it was very rare. So he says that all the mass of the atom is condensed in the center of the atom, and he called that nucleus of the atom. So he actually proposed a better model for the atom. Says that the mass is condensed in the center. Most of the atom is empty space, and it is mostly empty space. And also the deviation or the charge, since it was the alpha particle was moving away from the center, it was repelled by the nucleus of the atom, says that the positive charge should be condensed in the center also. So that those are the result of his experiment. So it says atom's positive charge is condensed in the nucleus. Protons has a positive charge. Electrons, they have negatively charged. And he was able to actually calculate the mass of the proton. Mass of the proton, it's much larger than the mass of the electron, because mass of the electron is like 10 to negative 28. Mass of proton is 10 to negative 24. It's like much heavier than the electron. So the mass of the electron, actually what's responsible for mass of the electron was the protons at the time of Rutherford. Later on, they also found the neutrons, and then because it didn't match with the mass of the atom, did not add up to the mass of the atom with the mass of the protons. They said there is a neutral component also in the nucleus that has the mass, but there is no charge. So charge of the neutron is 0, charge for proton is positive, charge for electron is negative. So this what was found, the neutrons actually were found by different scientists. Chadwick found the neutrons, and then you have like a summary table for what you need for so unless the question is coming specifically from Rutherford experiment, the history of how they come up with this is going to help you with understanding how scientists work, how chemistry works. I mean, what are the steps of the scientific method and all that. But after this chapter, after the first, first part of the chapter, you are going to deal with this table, which is the summary table only. So based on this summary table, electrons, they have charge of negative, protons, they are positive, and then neutrons, the charge of 0. The charge is like this is like the unit charge, okay, charge units. It's not expressed in coulombs because coulombs, scientists, they like to work with round of number and easier to work now set of numbers. So instead of giving the coulombs like every time minus 1.6 times 10 to negative 19. It says, okay, we're just going to say this is like a 1 unit charge for electrons. And that unit charge is negative, so it's a 1 minus. So protons, the same charge, is going to be opposite sign, but the magnitude of the charge is the same, is going to be +1. And neutrons, because they are neutral, there would be 0 charge. Mass of the proton is much heavier than the mass of electron. So when you account for the mass of atom, electrons actually do not contribute, so we don't have to worry about the mass of electrons, but protons would contribute and neutrons would contribute. They also came up with the atomic mass unit. Atomic mass unit would basically give 1 unit mass of 1 unit. So this is going to be atomic mass unit, is not gram. 1 atomic mass unit for proton and 1 atomic mass unit for neutron. And the mass of the electron was negligible because of the difference. Is like a 4, power of 4 difference in the mass. So it's ignored. So we have 1 AMU mass for proton, 1 AMU mass for neutron, charge of the electron, charge of the proton, and then you have the mass of the charge of the neutron, which is 0. You need to know these numbers. You don't have to remember the exact number for the mass, but you should have an idea. If someone asks you what's the mass of proton, as long as you don't say it's about like, it's very small, it's about like 1 gram, which is like that's a very large number for the mass of proton. As long as you know that you're dealing with like a minus 24 power, if you express in gram, then you're fine. You don't have to know exact number or exact mass. You don't have to memorize it. You just need to be able to, if this number is given, use it for the calculation, but you don't have to know the exact number. But you need to know the atomic mass unit, how many atomic mass unit each proton and neutron has. Okay, any questions?
No.
No questions? So what you see in the periodic table, you see cells, you see like groups, and you see columns, you see rows and columns, and each box you have 3 numbers or three characters. One is the symbol for the element, that's the X, and then you have a number, two numbers. Those numbers, let's say, if you see a number of one periodic table, someone decided to put this 235, okay, is a periodic table. In the periodic table still is valid. So I don't want you to memorize that the top number is always atomic mass and the bottom one is the atomic number. When you see a symbol in the box in a periodic table, the symbol actually represents the element, is name of the element, or the symbol for element is always indicated by either 1 or 2 letter. If it's just 1 letter, it's going to be capital. If it's 2 letter, the first one is going to be capital and second one would be lowercase. Like I told you last class, like if you have a C chlorine, the second one must be lowercase, because if you put both of them capital, this is a compound. You have carbon and you have oxygen. Is a carbon monoxide, is not cobalt anymore. So these symbols is either 1 or 2 letter, and the scientists who discovered the element had the choice of giving the name, and sometimes they give after the city that they live, or after the scientists who discovered. but or right now the names are presented to IUPAC. IUPAC is International Union for Pure Applied Chemistry. These are the people or chemists with like big hats. They meet annually or semi-annually, every 6 months in different country, and then they decide. They approve names. They deny. They make sure that anything that any claim has to go and approved by them, by this union, including the name. If you look at like a modern periodic table, you might see at the bottom level there are some boxes that they have numbers, but there's no name. What it means that that element was discovered, was synthesized, but there's still, the name has not been released yet because it needs to be approved. Or the time that the periodic table was actually printed, the name was not approved yet. So what are these numbers? Atomic number, atomic mass, and then the symbol for element. What counts for atomic mass?
It's the protons and neutrons added up.
Protons and neutrons. Very good. Protons and neutrons. So atomic mass, so if you have the symbol for the element, let's say you have carbon 12, and then if you just see carbon 12, okay, if you just see carbon 12, this is atomic mass. There is no need to put the 6. Periodic table, they use the 6, but in problem solving, there is really no need to say 6, because if it's not 6, if the atomic number is not 6, it's not carbon. So carbon 12, and then you have like carbon 13, that's the isotope of carbon 12. Atomic mass equals the mass of protons or number of protons plus number of neutrons. So atomic mass, let me use the next one. So atomic mass is basically 1 AMU. 1 AMU is defined as 1/12 of mass of carbon 12. Okay. So that's 1 AMU. So this, like, if you have a scale, then is better. So we already know what is the mass, the amount or the mass for in gram for 1 AMU. And that 1 AMU was assigned to the mass of proton. 1 AMU was assigned to mass of neutron. So since every proton is 1 AMU and every neutron is 1 AMU, if we know, let's say, one atom of carbon 12 has 6 protons and it has 6 neutrons, it has 6 electrons. Atomic mass is the number of, this equals the number of protons plus number of neutrons. Atomic number equals to number of protons. Okay, how do you find number of neutrons? Number of neutrons?
For this problem?
Anytime. Number of neutrons.
You can first find the number of protons, and then you would subtract it.
Subtract. Yes.
Yeah.
Subtract. You see, you have the atomic mass, which equals number of protons and neutrons. You also have the number of protons. So if you want to find the number of neutrons, the difference is going to be number of neutrons. Number of neutrons is going to be atomic mass minus atomic number. Atomic mass is protons plus neutrons minus atomic number is number of protons. So number of protons plus neutrons minus number of proton, it gives you number of neutrons. The electron, proton, and neutron, they are known as subatomic particles. So every atom is made of electron, proton, and neutrons. Let's say, what are the subatomic particles for this isotope of hydrogen? Okay, the hydrogen that you deal with is this. Deuterium, it's like only maybe like 1% of the hydrogen is deuterium. So it's not very popular. This is the hydrogen that you are working with, but these isotopes, they exist in nature. So we're going to just look for this atom or this isotope of the hydrogen and find number of, what's the first thing you want to find is the number of protons. What is the number of protons? Number of proton equals to what? How many protons do we have in there?
Just one proton.
Just one proton. We have one proton. Number of electrons is going to be, number of electrons is going to be always equal. So since I have here number of neutron is atomic mass minus atomic number. Number of electron equals number of proton, always. Because it's neutral, there's no charge. Number of proton equals number of protons. If you have one proton, then electron is going to be 1. And number of neutrons equals 3 minus 1, that equals 2. So what I was trying to say in the previous slide, I said when you see these symbols in the periodic table, it's not always the top number atomic mass, the bottom number atomic number. Is the smaller number atomic number, larger number is going to be atomic mass. It makes sense, right? Because atomic mass is protons plus neutron. Unless number of neutron is 0, the mass number would always be greater than atomic number. That's right?
Hey, Professor?
Sense? Yes.
I have a question. So you're saying that when protons and electrons equal the same, they will always be neutral, right?
Yes.
But if they differ, then they can differ, right?
They can differ in a chemical reaction, but not in the periodic table. In the periodic table, number of proton and electrons are the same. If you're talking about the atom, number of proton equals number of electrons. But if you're talking about ions, that's like ions form as a result of a chemical reaction. Like atom has to lose electron, gain electron to change to ion. And since for the ion to be formed, atom has to lose electron or gain electron, then the number of electrons is not going to be the same as number of proton. But for an atom without the charge, the atom that is sitting in periodic table, number of proton is always equal to number of electrons. And then it's going to be easy to find. So you take any element in the periodic table or any example like this, how many protons, neutrons, and electrons you have for carbon 14? Well, the answer is here, but if you didn't have the answer there, how would you find the number of protons? What number from this box shows number of protons?
Number 6.
The smaller number or the greater number? The smaller number, which is the atomic number. I'm just going to label this as atomic number. And that equals to number of protons, because atomic number is the same number of protons. And the larger number, the greater number, is the mass number. And this is the mass number. and that equals protons plus neutrons. Okay, protons, so we have the protons plus neutrons, and we have the protons from this symbol. How many electrons do we have? Number of electrons is going to be, so proton equals to 6, electron is going to be 6, very good. Electron is going to be 6 also because they are equal to the number of protons. And number of neutrons, we are still working on the same atom of carbon 14. Number of neutrons is going to be 14 minus 6, because 14 is number of proton plus neutron, and 6 is the atomic number, so it's just the protons. So in order to find the neutrons, you would subtract the two numbers to find the number of neutrons, and that equals 8. So we have number of neutrons, 8. Number of protons is 6, because the symbol is telling me number of electron is understood. So this part is understood. Electron is equal to number of protons. Number of protons, you have to memorize it. The smaller number is the atomic number, and that is equal to number of protons. The mass number is the total of proton plus neutrons, and you are going to find that from the when you have the total, then you can find the number of neutrons because you have the total and you have the part. That's like very similar to like if you have like 11 M&Ms, and what color are the M&Ms these days? You have like a red and blue M&Ms, and you have like 12 of them. If you already know 5 M&Ms is blue color, then the difference is going to be red color, right? That's basically the idea. You have the total and you have the part. In order to find the other one, you just subtract. Okay, subatomic particles for carbon 11. This is the carbon 11. This 6 is understood, that is 6 because this is assigned. Hydrogen is always 1. Atomic number of hydrogen is always 1. Helium is always 2. Lithium is always 3. Beryllium is going to be 4, boron 5. And we look at the periodic table, those numbers are always fixed. If you change the atomic number, the symbol has to change because they are assigned. You can use one or the other. Okay? You could say carbon, or you say an atom with atomic number 6. Then everyone who's taking chemistry class would know that that is carbon. An atom with atomic number 8, that is going to be oxygen, because that's where it says in the periodic table, atomic number for oxygen is 8. Okay, so now with the carbon 11, that's another isotope of carbon. The number of protons, that's number of protons, that's equal to number of electrons. So proton is 6. We have 6 protons. And since there's no charge here, I don't see any charge here, it's going to be 6 electrons. The neutrons are just going to be the difference, and it's going to be 5. Okay, we just saw carbon 11, carbon 12, carbon 13, carbon 14. We see like different isotopes of carbon, right? And then we said atomic mass is protons plus neutrons. Carbon, like carbon, if we just assume that carbon has 6 protons and 6 neutrons for carbon, then the atomic mass must be 12, right? But if you look at the periodic table, that's not, 12 is not recorded, is recorded as 12.01. Usually we use 2 decimal places. So you don't have to worry about the rest of them. Just 2 decimal places more than that. So how come you have fraction? Do we have like half proton or half neutron? We don't have half proton or half neutron, but instead we have different isotopes of the same atom. So if in the nature we have carbon 12, we have carbon 13, then we have to get the weighted average of the two, and that's what is expressed in the periodic table. This is like calculating your GPA. When you calculate your GPA, you took like 12 credit, and then for 6 credit you got B, for 3 credit you got A, and then for 3 credit you got C. Well, your average GPA is going to be calculated and calculated based on number of credits that you had, how popular was that number of credits, and then the grade for each credit. If you have like you take only 2 class, 1 lecture, 1 lab, and you get like A for lecture, you got B for lab, and then they say, okay, your average is 3.5, I'm sure you will be upset, right? Says, no, I had my 3 credit, I got A. My 1 credit, I got B. So it can't be 3.5. What should be? It should be closer to A or closer to B. It should be closer to A because your 3 credit course, you got A, and 1 credit, you got B. So your GPA should be closer to A. Same thing here. For calculating the average atomic masses, so you need to know naturally occurring carbon 12. You have, this is the mass, a percentage, 98%, 98.8% of the carbon is going to be carbon 12. Only 1.1% is going to be carbon 13. So if you are calculating based on only these two, the average that you're getting, it should be much closer to carbon 12. And you cannot say, okay, we have 2, 1 is carbon 13, 1 is carbon 12, and it's going to be 12.5. This is the mean average. Okay, but you have to do weighted average. So for the weighted average, you multiply the percentage. First of all, you change the percentage to decimal. So you divide by 100. Then you multiply the percentage by the mass of each isotope and you add them. So basically, if you have two isotope, you open like 2 brackets. And each bracket, you have the percentage in decimal. Okay, percent divided by 100 times mass of the first isotope, first iso. And then on the second one, percent divided by 100. Obviously, this is going to be the second isotope, right? Times mass of the second isotope. And based on this, you're going to calculate the weighted average. So first, change the percent to decimal. You see the difference here is divided by 100. And then multiply by the mass. If the element has 3 isotopes, what would you do? If it has 3 isotopes, then you open 3 brackets. And each bracket is the characteristic for each of the isotopes. Percent mass of first isotope, percent mass of second isotope, and percent mass of third isotope. And that gives you the weighted average. And the weighted average is what is reported in the periodic table, not the mass for one isotope, because your element has more than one isotope. Okay. So we look at the periodic table. I think after this, whatever I cover, it's covered better in the other presentations that I had for the already pre-recorded and posted. But since we have more times now, I'm going to continue. But I want you to check both presentations to be prepared for the assignments, or for the review, for the exam, of course, for everything, for all the assessments that you have. For the periodic table, the modern periodic table, the elements are arranged in a table based on increasing atomic number. Going from left to right, the atomic number is increasing. So the first row, you have atomic number 1 and 2. Then it goes to atomic number 3, 4, 5, 6, 7, 8, 9, 10. Goes next row, it would be 11, 12, 13, 14, 15. That's how it goes. So every element, the atomic number for every element is 1 unit higher than the atomic number to the left, or compared to the element on the left. So it's going to increase by 1. So this is the modern atomic, the arrangement of the element in the periodic table. When the elements are arranged this way, they are going to, they found out that the elements in the same column, they have very similar chemical property in a way that it looks like they belong to the same family. They belong to the same family, or same group, and they called it groups. So elements in the same column in the periodic table, they're called like group. So we have group 1, group 2, group 3, 4, 5, 6, 7, 8. And each group, or some of the groups, they have like a specific name. Others, they're just group 3A, 4A, 5A, 6A, 7A, 8, or 8A. And the period is the horizontal, of course, row of the periodic table. So you have the groups, and then you have the periods. In the elements in the same group, they have same physical property. If you look at the periodic table, this periodic table that is color-coded, it's basically divided by the elements, divided by metals and non-metals. And then this color, the gray color, actually these elements that they're separating the metals from non-metals, these elements located immediately on the side, they are known as metalloids. And metalloids, they have some characteristics from the metal and some characteristics from non-metals. So metals, bulk of the periodic table, they're all metals. Metals, they're solid at room temperature, except for mercury. And non-metals, they could be solid, liquid, or gas. Group 8A is very special. They're known as noble gases. They are very stable elements, and they are the role model for every element in the periodic table. So we talked about the groups, we talked about the periods, and then we talked about the metals and non-metals. And elements, they are similar to both, they are metalloids. And slide number 20. Some groups, they have a specific name, like group 1A, they have alkali metals, group 2A is alkaline earth metal, and group 7A halogens, group 8A noble gases.